With respect to what we're going to cover in class, we're just going to make two minor modifications to the single reaction versions of our material and energy balances. And they're the same corrections that we already saw for the batch reactor. So there's not a lot we're going to have to derive. We're just going to switch things around like this. We will primarily spend, after we introduce those corrections, we'll spend today and Wednesday going over examples of stuff in packed bed reactors, various examples, but we're not going to look at any more new equations because you now know all the equations for plug flow and packed bed reactors. There's nothing left. There's material balances, energy balances. Technically there's a momentum balance in there through the pressure equations, but those are always given to you, so there's nothing new. The multiple reaction stuff is in Fogler 8.8. Again, there's not a lot of derivation that comes from multiple reactions. We just tack on a few extra terms for anything that's there because of a reaction. And this little discussion should give you enough to finish problem 5.5 on your homework, which is making problem 5.4 a multiple reaction system. If you are curious or bored or whatever the right word is, your book has a lot of good problems that are multiple reaction with heat effects. Or just generally non-isothermal reactors. So if you look in chapter 8, any of the problems that are either 8-8, 23, 24, 25, and 26, if you feel like you need more practice on one of these multiple reactions in one of these kinds of reactors, these are all good practice problems. A couple of them, I think there's only like less than half a dozen problems in the book that have a difficulty ranking of D, which is their hardest ones. I think 25 or 26 is D, so it's a pretty hard one. The other ones are fairly standard for the types of homework problems that we would have, but they're also good practice because they ask for things that I don't typically ask for or in the way that I ask for them. So for example, either I think 23 or 24, or maybe it's the other one. Yeah, I think 23 asks for, here's a bunch of information, tell me the activation energy of a reaction, which is something we've never done before. So it gives you a profile, and you have to look at some point in the middle of the reactor and understand these equations enough to figure out what's the activation energy. Normally, we're just interested in the flow profiles, so that's an interesting variation on our normal problems. So before we get to these key ideas for 14, just a few things that we had for lecture 13 that we didn't have enough time to get to on Friday. So when we were done on Friday, we had stopped with the energy balance on a plug flow reactor of dt dv was equal to the Q plus RA delta H divided by the sum of the flow rates times their molar heat capacities. This was specific to a plug flow reactor, so this was our energy balance on a plug flow reactor. It was for one reaction, and we'll see the other one today, and with no shaft work, because none of our stuff has shaft work. The only other equation we needed to add to this was what happens for a packed bed reactor. The only thing that changes for a packed bed reactor is you switch from volume to weight, or you can actually go the other way from weight to volume. So the conversion factor that we saw was the weight of catalyst in a bed is equal to the density of the bed, rho B, or rho bed, times the volume of the bed, or volume of the reactor. So if we take that conversion factor, we can put that inside of our energy balance for a plug flow reactor. If you take the derivative of W with respect to V, then you'll get rho bed times the derivative, or the change in volume. And then we can substitute that into our expression for the change in temperature. If you apply the chain rule, you get something like dt dv, v. That has to be equal to dt dw times dW dV. That's an application of the chain rule that, I don't know, maybe you haven't seen it written like that before, but it is still the chain. There's actually a lot of different ways you can put that substitution in there. That's one way to do it. And then dW dV is just equal to rho bed. So we've got that times dt dW. So anywhere that we see dt dV, this term, we can replace it with this term, which fortunately only shows up over here on the dt dV term. So we're going to substitute that in there and then divide both sides by rho bed. So the rho bed will go away on the left. What will RA become? Just RA prime. The only oddball term we're left with is that Q dot parameter, which just has to get divided by rho bed. There's not really a simplification for that. You just end up with rho bed. So the end result is dt dW is equal to Q dot divided by rho bed plus RA prime times delta H over the same term in the denominator. Right, and that's the only modification that we have if we need to do a packed bed reactor. So this is our same energy balance on a packed bed reactor. Again, for one reaction. So you can see if it's an adiabatic reactor, then it looks almost identical. We just switch W's instead of V's and RA primes instead of RAs. But that little business with the Q's and the rho beds, don't forget that, because otherwise your units aren't going to work, and nobody wants your units not to work. Any questions on that? You could repeat the whole derivation for the plug flow reactor for the packed bed if you want. You should end up with the same thing, but it's just as easy to start from the PFR and make that substitution. And that's it. Those are the only equations that we have for the energy balances for packed bed and PFR. Keep in mind a couple of the oddities about these terms. This delta H has to be evaluated at whatever the temperature of the reactor is. So this, not just that delta H, that's the same as this delta H up here. So keep in mind that anytime you want delta H, that's going to be equal to delta H at some reference, which we'll put the circle on there, because usually it is the circle, it's the 298.15 that we have access to, plus a delta Cp times T minus Tr, where this Tr is whatever the temperature of that delta H is at. What are some ways that we might expect delta H to be approximately constant based on that equation? There's about 3. Yeah.
Isothermal reactor?
It could be an isothermal reactor. If it's an isothermal reactor, then this term goes away. Actually, it doesn't go away. If it's isothermal at what temperature?
The reference temperature.
At the reference temperature, yeah. If it's just plain old isothermal, you might have to still make that adjustment, but you'd only have to do it once at the beginning. What's another way that delta H could be approximately constant or exactly constant?
If delta Cp is 0?
Yes, if delta Cp is 0, and how could we come up with a constant delta Cp?
I don't actually know.
So it's not a trick question, but there are many different ways you could come up with delta Cp. 2 that I can think of. Either the heat capacities are the same and the stoichiometry is the same. So if you have A goes to B and the heat capacity of both A and B is like 30 kilojoules per mole per Kelvin, then that delta Cp will be 0 because you'll have 30 minus 30. You can also have odd combinations of stoichiometry and heat capacities to make it also equal to 0. So like 2A goes to B and one of them's 30 and one of them's 60 for heat capacities. It just so happens that delta Cp could be 0. So you could have delta Cp is equal to 0. You could have T is equal to Tr. There's one more way. Both of those would make that exactly equal to 0, and therefore delta H would be exactly constant. What's one way that it could be close to constant? If we have delta H is approximately equal to delta H0, then that means what about delta Cp times T minus Tr? It's approximately equal to 0. That's one way that we could have done it, but that's roughly what we were saying with our other discussion, right? If the delta Cp is exactly 0, or if it's close to 0, or if T equals Tr is true, that's also a case when we would have that. In general, if that term is much, much less than delta H0. So delta H0 might be on the order of 100 kilojoules per mole. If you were to get something like a delta Cp of maybe around 10 or less, then that is going to look much, much less than 100. So there's some engineering judgment that goes into it. If I calculate that Cp, or delta Cp times T minus Tr, and I find out this is a very tiny number for any relevant temperature inside my reactor compared to something like delta H circle, then maybe just to get started to make progress on a problem, if I'm not worried about the exact details of it, then I can get rid of that delta Cp times T minus Tr term, just to make my life a little bit easier. But it is an approximation. Delta H is never exactly 0, or sorry, never exactly constant. So those are just some comments on the delta H term up there. Where does the inert impact the temperature in the reactor? In the what? In the bottom, right? It only comes into the Cp term here. This term has nothing to do with inerts in most cases, because that's talking about energy that I'm putting into the system or removing from the system through the walls of the reactor. So that's this term, in case you're on the podcast. This term, the Ra delta H, only has dependence on something that participates in the reaction. So generally, your inerts will not impact that rate. Asterisk, that we'll get back to in a moment. Generally, the inerts only enter through this term, right? Because that term doesn't care whether or not something is participating in a reaction. If you're there, you must have a heat capacity, and therefore you can sit there and absorb energy. And typically that results in slowing down the rate of change of temperature as you go down the length of the bed. In fact, not typically. Both of those numbers always have to be positive, so it always does that. One thing that I just said, which was an asterisk on the Ra delta H term, this one. It is possible for the inert to enter in there, but only for a non-elementary reaction. Most of the reactions we deal with, certainly on a regular basis, are going to be elementary, and therefore inerts don't participate, because those normally would not participate in an elementary reaction. If you look in your project, however, some of the rates that you're going to be dealing with are pretty non-ideal, non-elementary, and those will have a dependence on whether or not there is an inert in there. The origin of that comes not from the molecules reacting, but because the molecules that are reacting have to diffuse their way down to a catalyst surface. So we saw those catalysts on, I think it was Friday I passed around the catalyst, or Wednesday, the little tube of catalysts. They're pretty porous, right? So you have to eventually get your reactant into those catalysts, and that can take time. If you put an inert in your system, typically that builds up around your catalyst, just like it would anywhere else, and now your molecule has to make its way through all of that inert, which can kind of slow everything down. And you'll see the effect of that in, if you do I think the primary reactor in the project, the blue project, has a term inside the rate that is dependent on whether or not you have inert. So in most cases, that Ra delta H term has nothing to do with inerts, unless you've got a somewhat unusual non-elementary system. But for most cases, that's going to have nothing to do with inerts. Any questions on our equation down here for energy balance? there is an odd thing that happens with an adiabatic reactor that we've already seen previously, which is sort of a special case. It's not really a special case unless you consider adiabatic a special case, but among other things, if you can have an adiabatic system or approximate your reactor as adiabatic such that your Q dots are equal to 0, and you can have no shaft work, and you can have delta Cp equal to 0, and now it's a fairly special case. If Cpi are all constant, and just keep in mind Cpi being constant and delta Cp being constant, or delta Cp being 0, those don't necessarily go hand in hand. You can have Cpi be constant and not have a delta Cp be 0. It's kind of hard to do it the other way around, but at any rate, if you can have all of these, and you can have one reaction. So that special case looks like, well, that probably never actually happens, right? It's pretty rare to get all of those to come together. However, if you do have all of those, you can learn something about your system because you can develop an analytical expression between temperature and conversion. And that analytical expression is something that we're going to spend some time with in the design portion of the class. So we've got about another week and a half or 2 weeks of flow reactors, and then we've covered all the standard reactors we're going to cover, and we get into the design portion. And a little bit of intuition from this specialized case can go a long way in designing a reactor, because as you'll see in the problem, which this one I think is the ammonia reactor, even if the system is really complicated, you have non-ideal or non-elementary kinetics, you have pressure dependence, you have all sorts of things that make it more difficult than this, the end result is it behaves basically like this. Despite all those complications, most reactors, at least qualitatively, will behave like this. The qualitative dependence that I'm talking about is if you have all of these, you can solve the energy balance. You'll also have to use the material balance to get something that looks a little bit simpler, which is that the conversion of A is equal to the sum of the theta i's times Cpi times T minus T naught. T naught is the inlet temperature, not the reference temperature. All of that divided by minus delta H. Your book puts a little superscript on this called EB, just to remind you that this is the conversion of A derived from the energy balance. I repeated the derivation that the book did. It takes about 2 pages, so we're not going to go over it. We're just going to drop that equation on you. The reason that this is particularly nice is what we saw with the batch reactor, which is that this predicts that temperature on the x-axis and, oddly enough, xa on the y-axis with EB on it, is going to be a straight line. Right, so if this is 0, then you'd be starting at your inlet temperature down here. Because that is a straight line, as we're going to see when we get to the design equations, we can make some qualitative estimates pretty quickly without having to actually solve all those equations, just by knowing that conversion is linearly related to temperature. And as you'll see in the project, if you choose to do the ammonia one, even when they're not linear like this, even when we don't have all those assumptions, simply by, I won't say luck, but because this is not luck that we ended up with this, it just so happens that even a lot of real systems end up with an approximately constant line through there. So a real system might look something like this, right? So it has a little bit of curvature on it. It still looks pretty close to linear. And that's something that you'll play around with in the project, and the utility of that straight line will become a little bit more obvious when we get to our design equations. The 2 topics, since we're getting close, I might as well tell you these 2 topics. One of them is if we have something that's called multiple steady states. So in the reactors we're dealing with right now, we can't have multiple steady states. Well, no, I guess you could. We just don't. In the other kind of reactor we're going to introduce later this week and into next week, you can. The other thing that you have, which appears in your project, is a concept called interstage cooling or interstage heating. Both of these, so interstage cooling or heating means I have a reactor bed, I run stuff through a bed, I get it out of the bed, and then I run it through a heat exchanger to either heat it up or cool it down, and then I put it into another bed, another heat exchanger, another bed, another heat exchanger, another bed. That's what's called interstage heating and cooling. Either one of these topics, the multiple steady states or the interstage heating and cooling, you can solve the full version of the equations as we've been doing up until now. But as we'll see, this concept can give us a lot of insight into what's happening in those systems. And so we'll make use of that, even though most of our systems cannot be simplified in this way. They can be well approximated by the behavior of a system that has been simplified in this way. So I think I brought that up in the batch reactor and said, we're not going to use it right now, but keep it in mind. I'm bringing it up again now to say we're not going to use it right now, but keep it in mind because in about 2 weeks we will use it. Interestingly, this equation is the same. If you go look at the batch reactor, it's the same as what this is. So it's the same for batch, plug, packed bed, and as we'll see next week, it's the same for the last type of reactor, which is CSTR. That's one of the reasons it's so useful, is because under those conditions, all the reactors look basically the same in terms of conversion. Conversion is a function of temperature. Any questions on that bit? Kind of something to put, if you can write in 2 different shades of pencil, put that as a lighter shade off to the side, because we're going to come back to it. Yeah?
The reactors will also make the same assumptions, right?
Yep. All right, so that covers everything that I wanted to talk about on Friday that we didn't get to. The topic for today is the multiple reactions for either a packed bed or a plug flow reactor. And as I mentioned on the key ideas sheet briefly at the beginning of the lecture, there's not a lot of changes that we have to make to this, and we've already seen all of these changes for a batch reactor. So if we're worried about multiple reactions, in either a PFR or a packed bed reactor, we have 2 changes to make. One is to the material balance. The change to the material balance is the same as the change that we saw before. Instead of writing a single R sub I, we have to write that R sub I as the sum of the rates of reaction for species I in all reactions J. So J equals 1 to, I think I used Q as the number of reactions. That procedure looks identical regardless of whether you're dealing with a packed bed or a plug flow or a batch reactor. The other change that we have to make is we now have multiple reactions going on. So if you're dealing with a plug flow reactor, this RA delta H term is also going to become a sum of Rij delta H. Again, for J is equal to 1 to Q. And keep in mind that this I term, actually there should be an Ij on this too. The I and the J means any reaction, so normally we number our reactions 1, 2, 3, 4. The I can be different species depending on which reaction you're talking about, because not all species have to participate in all reactions. So you just have to set up the Rij's times the delta Hij based on whatever that reaction looks like. I've got an example that we'll get to in a minute that'll help you practice that a little bit. The other variation that we have is for the packed bed reactor, which is the same except instead of Ra we have Ra prime. So we used to have Ra prime times delta H. This, for a multiple reaction system, is going to become Rij with a prime times delta H, Ij. And again, that's for all however many reactions you have up to Q reactions. And that's it. Those are the only two changes that we have to transition from a single reaction to a multiple reaction. The only downside of the multiple reaction systems is we generally can't express anything in terms of conversion when we're trying to solve the problem. We only get to conversion when we're all done because we write the material balances and the energy balances only in terms of the molar flow rates F. You can also do it in terms of the concentration, but not X sub A. So we're going to write the energy balances and the material balances using Fi or Ci, but not Xa. We can still define conversion as needed, which also, if you haven't checked your email and you haven't checked TED, there was a typo on problem 5.2 where I kept mixing up butadiene and butene. Make sure you read that so that you know which way it's going. Somebody emailed me and had a good point, which is I can write the conversion of the products if I want. I can write everything in terms of conversion of products, but then it goes negative, and we don't often write conversion as negative. But mathematically speaking, you can do it. We just don't. Similarly, for a multiple reaction system, if you didn't want to write it in terms of conversion, you could write it in terms of the squiggle, the extent of reaction. It's just nobody does that because you're going to have to solve it all in MATLAB anyway. So it's just more options for you to make typo mistakes when you're converting from written to code. So anytime you have to solve one of these, you're almost certainly going to have to write everything in terms of the molar flow rates or the concentrations, either one of those. If you need to calculate Xa, we would get this after solving the problem. Any questions on multiple reactions? Looks like it takes up a lot more space in the syllabus than it really does because one slide and we've done everything for multiple reactions. Okay, so let's look at an example, or better yet, you're going to look at an example. I'm going to give you the example. And since we don't have MATLAB in front of us, or at least most of us don't, and I'm not going to sit here and code because that is boring for everyone involved. We're just going to look at various portions of this that you have to develop before you ever get to writing it in MATLAB. So if we have two reactions, and one of them is A plus B goes to 2C, these are both going to be irreversible for the moment. And another one, 2B plus C, goes to D. And we're given the rate laws for these. So we have R1 in terms of C is equal to K1C times CA CB. We also have R2 for species D is equal to K2 species D times C sub B times C sub C. Notice that which one of those is elementary and which one isn't. The first one is elementary, or at least it appears to be elementary. The second one is not elementary. Which is okay, right? If I give you a rate law, it doesn't really matter then what the stoichiometry of the problem is. You just use the rate law like that every time. This one, by the way, the second reaction here, if that were elementary, then there should have been some concentration of B squared, and B is not squared in our system. And then we have one additional parameter for each one of these, which is that delta H for reaction 1 in terms of species A at some reference condition is equal to minus 50 kilocalories per mole A reacted. And similarly, delta H for reaction 2 in terms of species B at our reference condition is equal to plus 5 kilocalories per mole B. So this is pretty standard in the sense that it doesn't matter if I'm going to solve the system with MATLAB or if I'm going to try to do something by hand. There are a couple of steps that we will probably have to do regardless of what that solution method is. The first step that we have to do is to write the net rates for each species. This should be pretty similar to what we saw in the batch reactor, which means I'm going to get out my phone and I am going to give you 8 minutes. You are welcome to work with anybody around you, but practice a little bit here and see if you can write the net rates for all the species. So there's 4 species involved here, A, B, C, D. Write the net rates for each one of those. I'll start the timer. We should have enough time. We'll take 8 minutes and see what you can do with something like that.
What type of reactor is this?
This is plug flow. So that was only about 5 minutes. I will start talking now since I think most of you were there. Normally when I have to write a set of rates down like this, the very first thing that I write is the stoichiometric relationship between all of the rates for a given reaction. Keep in mind that, actually, show of hands, does this expression that I'm about to write here, let's take a look at reaction 1. So if I wrote R1A over minus 1 is equal to R1B over minus 1 is equal to R1C over plus 2, does that reaction depend on the stoichiometry that I chose? Am I allowed to change the stoichiometry of the reaction as given and still write something like that? I could write something like that, but I can't write that. If I change the stoichiometry, then these numbers will change down here in the bottom. Right, if I divide everything by a half, all of those are going to get divided by a half as well. But I can write it in terms of whatever the stoichiometry is that I'm given over here. Or if you have something like equation 2 and you don't like this 2 sitting out front, you can divide everything by a constant and then rewrite that equation that we just saw. So the choice of stoichiometry in this problem, or the stoichiometric coefficients, has no effect whatsoever. Why doesn't it have any effect? Where's the only time the stoichiometry has an effect? In the rate law, right? If I said that these reactions were elementary, you would need to know what the stoichiometry was, or it was given to you in some different way, in order to figure out what the rate law is. Here you've been given rate laws. One of them is non-elementary for 2D. So we're just going to use that reaction rate in the way that it's given. Which means, now that we have our rates, remember that's the only place stoichiometry is important, we can change the stoichiometry to anything we want for the rest of the problem. It just so happens that the stoichiometry for these aren't awful, so I'm going to keep this stoichiometric relationship the way that it is. And like I said, normally I will start off writing one of these stoichiometric relationships for each equation, or sorry, each reaction. So that was for the first one. And then the second one would have been the rate of reaction 2 in terms of B over minus 2 is the rate of reaction for 2 for C over minus 1 is the rate of reaction for 2 in D over plus 1. The next thing I do, and if you look at my notes for these sorts of things, is circle the ones that are important. The ones that are important are the ones that we're given rates for. Or if we had to derive those rates, we probably wrote them in terms of a specific component. So for the first one, we had R1C was the important one. And for the second one, R2D was the important one. Notice that if A is our primary reactant, it never shows up in the second expression, so whatever, quote-unquote, the important one is, can vary from reaction to reaction. It doesn't have to be the same species. And then the method for developing the rates, I'm only going to write 2 of the rates here, not all 4 of them, just so that we can practice the next step a little bit. Is to pick every species, so let's say R sub A, and write down that reaction rate for each species. So the brute force way is to write R sub 1A plus R sub 2A. If we had more reactions, then it could look something like 3A and 4A, all the way up to the Q reaction, right? If you want the brute force method, you just write it down regardless of whether or not that species shows up in that reaction. As it turns out, A doesn't show up in one of these reactions, so we would get rid of this term. And R1A, if we look up at our relationship, R1A is over here, so we need to relate that to R1C. Which is going to be, according to those numbers, minus 1/2 R1C plus 0. And 1/2 times R1C is going to be minus 1/2, sorry, minus 1/2 R1C is minus 1/2 K1C CACB. I'm going to do one more for B. And then if you haven't gotten a chance to finish C and D, you can finish those up afterwards. Remember, the brute force way is just assume B occurs in all of the reactions. R1B does occur in reaction 1, which is here, so I need to write that in terms of R1C. And R2B does react in reaction 2, so I need to write that in terms of R2D. So if I look at R1B, according to that stoichiometry, there's another minus 1/2 sitting out front. So minus 1/2 R1C. And if I look at reaction 2B, that's going to have a minus 2 in front of it. So minus 2 R sub D. Not just D, 2 R sub 2D. So that'll look similar, minus 1/2 K, what did I call it, 1C times CACB, minus 2 times K 2D C sub, where's my rate? B and C. And then I would end up doing the same things for RC and RD. If there's an inert present, what's R sub I? 0. Which can be useful if you've ever got a large system of equations and you, for example, vectorize them in MATLAB. You can include something like a 0 rate in there just to remind yourself that it's inert. The next step for the multiple reactions is to write the other thing that depends on react. Actually, before I go on, any questions on what I wrote there? Or any mistakes? Please tell me if I make a mistake. All right. The next step, so take about 3 minutes to do this one, is to write the sum of Rij delta Hij. So it's 12:45 now. Take 3 minutes and work on those. First, how many of those terms should you have? 2, right? There's 2 reactions, so there's 2 delta H's. All right, the general pattern for these is the i's and the j's have to match. The choice of which one is easier for you, do I start with an Rij and use that and make the enthalpy match, or do I start with the enthalpy and make the Rij match, is up to you. You will end up getting the same answer either way. I typically find it easier to start with delta Hij. Take that as given and switch the rate around. The reason being, I've already done that math over here. I already know how to relate one rate to another. Then I don't have to keep an additional process in my head that says, how do I convert one enthalpy to the other? So if I wanted to start off with this, I need it from 2 reactions. The first one is given as delta H of 1A. So therefore, the rate has to match both of those subscripts. So I'm going to need an R sub 1A for that as well. Similarly, for the second reaction, I'm given a delta H as 2B. So therefore, the rate has to match, which is R sub 2B. R1A, according to that stoichiometric relationship that I had a moment ago, is equal to minus 1/2 R1C times delta H1A. That conversion factor of 1/2 is going to show up either because you made the rate match the enthalpy, or if you had to make the enthalpy match the rate, the way that you would do that is to convert, because your enthalpy, keep in mind over here, or sorry, here, how we wrote the enthalpies. It's per mole of A. Specifically, it's per mole of A reacted. So if I needed to know how many moles of A were reacted, or more specifically, if I needed to know how many moles of B were reacted, that is stoichiometrically proportional to the moles of A reacted. So that stoichiometric coefficient would have to show up on the delta H if that was the one I choose to adjust. I usually don't choose to adjust that because it's one more adjustment that I have to keep in my head. So I usually will adjust the rates as we've done here, such that R1A is minus 1/2 R1C and R2B is minus 2 R2D. Times delta H2, or no, yeah, that's right, B. So those sorts of adjustments, even if I can't ask you to hint solve one of these problems analytically on an exam, I can still ask you to write stuff like that. So that process is something that you have to do regardless of how many reactions are in there. So try to get somewhat comfortable with that. Develop a scheme that works for you that you can apply to all of these. I like the way that I did it, but it's not the only way to do it. So that's all we got. I will see you on Wednesday.